Hi there. In this lecture, we're going to see two types of scheduling approaches that are very popularly used with Hadoop clusters today. So a Hadoop job, if you recall, consists of map tasks and reduce tasks. When you have one job in the cluster, and that's the only job in the cluster, its tasks can occupy the entire cluster. So different resources in the cluster can be allocated to that particular job's tasks. However, you might have multiple customers with multiple jobs, and these users, customers, or jobs are known as tenants in the cluster. So you have essentially a multi-tenant system where there are multiple tenants occupying the cluster and competing for resources that the cluster has. So you need an approach or a strategy to schedule all these jobs from across the different tenants. And when I say schedule jobs, I essentially mean schedule the tasks that are inside these jobs. And sometimes you want to be fair across the different tenants in your system. You don't want to give one tenant much more resources than another tenant. You do not want to allow one tenant to completely hog your cluster and deny access to the cluster to the other tenants. So Hadoop Yarn has two schedulers that are very popular with installations today, the Hadoop Capacity Scheduler and the Hadoop Fair Scheduler. We'll discuss the Capacity Scheduler first and then the Fair Scheduler. The Hadoop Capacity Scheduler contains multiple queues. If you recall from our discussion of single processor scheduling algorithms, the queues essentially contain jobs. So each queue contains multiple jobs. Each queue is guaranteed some portion of the cluster capacity. For instance, you might configure your system with two queues, Q1, which has 80% of the cluster, and Q2, which has 20% of the cluster. And in this case, you might have the higher priority jobs in your system go to Q1 because it has a lot more of the resources in the cluster. For jobs that are within the same queue, typically first in first out scheduling or first come first served scheduling, FCFS, FIFO FCFS is used. This is again something that you have seen in the single processor scheduling approach. But essentially what happens here is that a job that arrived earlier would be given resources first. So whatever resources it needs for its tasks, it's given first. And then when that job is done, the next job in the queue is taken and given resources. If the job is not able to fill that entire queue's capacity, for instance, if a job in Q1 occupies only 40% of the cluster, another job can be allowed to run concurrently with it in Q1 itself. So FIFO is typically used, but again, it's not necessarily used. You could modify the Hadoop Capacity Scheduler to use a different approach. Administrators are allowed to configure the queues, these queues that I've discussed. So you can configure each queue to have limits. There might be a soft limit, which specifies how much percentage of the cluster resources that particular queue is guaranteed to occupy. Optionally, you can also specify a hard limit, which is the maximum percentage of the cluster resources that that queue is guaranteed to occupy. So this means that the queue cannot cross the hard limit. So if the hard limit is 90%, it means that that queue cannot ever be given more than 90% of the cluster resources. Elasticity is allowed by this particular approach because if, for instance, there is only one queue that has jobs, then the queue might expand as much as possible to occupy the entire cluster. So if your hard cap, for instance, your hard limit is 100%, then that queue could be expanded to occupy the entire cluster, and its jobs can get the entire cluster as long as resources are free. But if there are other queues in the system that are below their capacity limit, so for instance, if another queue had a soft limit of 20% and it is running at 5%, it now needs to get more resources because, for instance, it might be having more jobs. That other queue may need to be given resources, which means that this queue that is currently occupying the entire cluster needs to give up some of its resources. So one way to do this might be to kill the tasks in that queue, but that's not what is done in the Hadoop Capacity Scheduler approach. Instead, you do not allow preemption at all because you do not want to waste tasks that are sort of partway through. You don't want to kill any tasks. Instead, you simply wait for those tasks to finish. When a task finishes, you take away that part of the resource from the first queue and give it to the other queue that is now requiring resources. So essentially, the elasticity or the scaling in portion here happens slowly as tasks finish. The resources are then taken away from that queue, which the tasks belong to, and it is given to the other queue that is requiring resources. Okay, so this approach here that you're seeing is slightly different in the Hadoop Fair Scheduler approach, which we'll see in a few slides. A few other features in the Hadoop Capacity Scheduler: the queues themselves can be hierarchical, so a queue might contain child subqueues, which may then contain child subqueues, and so on and so forth. And this is useful so that child subqueues can be made to share resources equally in between each other. So for instance, if a queue is given to one particular organization, that organization might have multiple departments, and these departments are each given a child subqueue. and these child subqueues now share resources equally among each other. Scheduling in the Hadoop capacity scheduler can also take memory requirements into account, where the memory is typically specified by the user. And as of this particular recording, the Hadoop capacity scheduler only supports memory as a resource being specified. It does not support multiple resources being specified. So let's look at the other scheduler, the Hadoop Fair Scheduler. Here, the goal is to target a multi-tenant system where you have multiple jobs or users occupying a cluster, and you want to ensure that all the jobs get an equal share of the resources in the cluster. But of course, when only one job is present, you want it to get the entire cluster if that job requires the entire cluster. So fairness does not mean you starve a job even though resources are available. However, as other jobs arrive in the cluster, each job is given an equal percentage of the cluster resources. For instance, each job might be given an equal number of cluster-wide yarn containers, where a container is a set of processor and memory resources that is enough to run one task of one job. Okay, container is a well-accepted term in yarn, which you have seen elsewhere in the course. So the Hadoop Fair Scheduler divides the cluster into pools, and typically there is one pool per user. The resources are divided equally among pools. This ensures that each user gets a fair share of the cluster, because each pool gets the same amount of resources. Within each pool, you can use either fair share scheduling, so all the jobs belonging to one user can either share resources fairly with each other, or you could use first in, first out, or first come, first served scheduling, FIFO FCFS, as you have seen before. This is also configurable. You can also configure what kind of scheduling algorithm you want to use within each pool. Some pools are specified, are configured to have minimum shares. This is the minimum percentage of the cluster resources that particular pool is guaranteed. When for a particular pool the minimum share has not been met for a while, then you take resources away from the other pools and you give it to this pool. And here the Hadoop Fair Scheduler differs from the Hadoop Capacity Scheduler in how it takes away resources. It takes away resources from a pool by in fact killing some of the tasks in that pool. In fact, it preempts the jobs in those pools by killing some of the currently running tasks of those jobs in the pools from which it wants to take away resources. These tasks can be restarted later anyway, and these tasks are idempotent. By idempotent, I mean that if you run the tasks multiple times on the same input, you're going to get the same output. So there are no side effects of these tasks. So killing a task partway through and then just restarting it later on the original input is fine. It leads to some wasted work, but this wasted work can be minimized by picking as a victim to kill some tasks which were started recently. So tasks that have only started recently are picked first to be killed, and then if you need to kill more tasks, you kill tasks that started farther in the past. This again minimizes the amount of wasted work, because tasks that started recently have probably done just a little bit of work, and so killing them will minimize the amount of wasted work. But it does result in some wasted work. There have been some proposals since then from the research community that have proposed, in fact, saving the state and then rerunning the tasks starting from their saved state. However, the Hadoop Fair Scheduler does not support that. A few other features in the Hadoop Fair Scheduler: you can also set limits on the number of concurrent jobs per user, a limit on the number of concurrent jobs per pool, and the limit on the number of concurrent tasks per pool. All of this prevents a cluster from being hogged by just one user or by just one job. It also prevents too many tasks or too many jobs of one user from competing for a small number of resources that are being allocated to that particular pool. So far, we have seen that Hadoop Capacity Scheduler and Hadoop Fair Scheduler tend to use the FIFO, or the first come, first serve, or first in, first out approach, FIFO FCFS. But as we have seen in the previous lecture in the series, FIFO is not necessarily optimal as far as completion time is concerned. And the question might be arising in your mind, why not use shortest task first instead? In fact, that is optimal, right, as we know it. The challenge with Hadoop is that it's hard to estimate the expected running time of a task before the task is actually completed. Right? So it's hard. So when tasks are generated by a Hadoop job, the tasks do not come specified with the exact time that the task is going to run for. Okay? And as a programmer, you don't know that either. So a way to combat this, to address this, and so that you can use algorithms like shortest task first, is to estimate the task length. Okay? So a few approaches that can be used. So within a job, you can calculate the running time of a task, or estimate the running time of a task as being proportional to the size of its input. So if one particular job with a 1 megabyte input took 20 seconds, one task with a 1 megabyte input took 20 seconds to compute, another task with a 2 megabyte input twice the size of the first task, will take 40 seconds to compute. You can also do the estimation across jobs, where you can calculate the running time of a task in a given job as the average of other tasks in that given job. So you can take the average running time across all the tasks in that job that have completed, and then based on that you can calculate the running time of a task. And then also you can weight this by the input size of that particular task to get a more accurate running estimate. But of course these are only estimates, and so they may not actually be true, and so you may not actually get an optimal running time here, even though you're using shortest task first, because the estimates may be off. Okay, there's been a lot of recent research results and research work in this particular area here. So to wrap up a discussion of Hadoop scheduling in Yarn, we have discussed two schedulers: Hadoop Capacity Scheduler, which tends to be the default scheduler, and the Hadoop Fair Scheduler, which is used in a variety of different scenarios and a variety of different Hadoop clusters. Yet so far in this lecture and the previous lecture, we've only talked about one kind of resource. In the previous lecture it was processor. In this lecture it's predominantly memory. But typically jobs such as VMs, for instance, have multi-resource requirements. Some jobs may have some CPU requirements and also some memory requirements. And how do you handle these? We'll discuss this in the next lecture.